Hi guys, and welcome to the video for graphs of the differential function. My name is Darren from Maths Guru. Thanks very much for watching. If you're new to my channel, do me the favor, please, of subscribing to my YouTube channel. That single click from you actually means the world to me. So very few people watch maths videos that sometimes I sit in a room and go, what am I doing with my life? All right, I could actually be outside in the sunshine and not look quite so pasty. But if you actually are watching this video, then hopefully you're getting value from it and can just subscribe. Turn off notifications if you need to. Trust me, I don't spam you. But it's just great to know that people are watching. Follow me on TikTok, and all the things you see behind me at this moment in time, which I write all over, you can download from mathsguru.com, which again is totally free to sign up. It's got videos, exam questions, and all sorts of things for you as well. Now, what are we dealing with this lesson? Well, it's building on what we've done before. We already now know the basics of differentiation. It's important to note that when we do these type of things, everything is a function, it is a graph, it is some sort of relation that we need to look at. And a lot of people, when they do these type of questions, go, oh, yeah, and you do the mechanics. You multiply the power, take one off the power. Multiply by the power, take one off the power. It's really important that you actually understand why you're doing it. You're finding gradients at points. You're trying to sketch curves. And really, the methods course, if you haven't already worked that out, is massive on sketching curves. So by the end of this, we want to know what's meant by the sign of the derivative, what strictly increasing and decreasing is, what is meant by a derivative test, and finding an angle associated with the gradient of a curve at a point. Okay, very exciting. Now, if you don't know the fundamentals of why we differentiate or how to differentiate, please stop now, go back and watch the video. If you're sorted with that, we can pretty much move on and talk about the sign of a derivative. Now, obviously, the whole point of deriving is to find some sort of function. It's to find the gradient of a tangent at a particular point, right? We can find the gradient function, which will give you some sort of idea of how to find the gradient given an x value, or we can find it at a specific point. Now, if we actually look at this point here, for example, and try to draw a tangent to it, then we're going to end up with a line roughly like that. Now, if I was to ask you what is that, a positive gradient, a negative gradient, or a zero gradient, hopefully you would all turn around and say that's a positive gradient, all right, because it's sloping up. What about if I was to choose this point here and draw a tangent to it? Well, in that situation there, we would see that it's a negative gradient. And likewise, if I was to take this point here and draw a tangent to it really badly, we'd notice that that was also a positive gradient. I can work different points along my line, finding out whether the gradients are positive or negative. Really important. But probably the one we use the most is a zero gradient, right? So in this situation here, at the very top, or the very bottom, or sometimes in the middle, we'll come back to that one later, there is actually a zero gradient. And differentiation is really good, because if we know that a particular point a gradient is zero, we can actually solve and find out where zero gradients are to help us sketch these curves. And again, more of that's coming on later. But the problem with methods is it uses a lot of terminology to try and trick you. Why? Who knows? Barry. And so in too many exam questions, I see things like that. And a lot of people then start to panic about that, saying, oh my goodness, I've got to find a value of f dash of x is greater than zero. That's not really how to read this. We can actually read that as positive. So when a number is greater than zero, all right, what they're really meaning in that notation is positive. So this is basically saying find where my gradient is positive. And there might be lots of points on the graph. And so we would use interval notation to try and denote those x values there, right? So when you look at these functions, really you're looking for positive gradients, negative gradients, zero gradients. And then if you've got that, believe it or not, you can draw some pretty good sketches. So here's an example, all right? Now for the graph of f, which is real mapped onto r, find this. So obviously this notation here, again, is there to try and confuse. It means find the set of values for x for where f dash of x is greater than zero, all right? So this is going to be an interval. We're trying to find out where my gradient there is going to be positive. So looking at this graph here, where is my gradient going to be positive? And the trick to this question is it's greater than zero. So we can't actually include any minimum points or maximum points. And again, I've used that language quite specifically because here at the very minimum, that gradient is going to be zero. And at the very maximum, that gradient is going to be zero as well. So we can't include that because it's going to be greater than zero. So I'm not asking myself now, where on there are all my gradients positive? Well, hopefully it's got to be between this line here, or that point there, and that point there. Now again, the reason they give coordinates is to try and trick you. Lots of people use the wrong values. I tend to scribble out the y values at this moment in time because it's the x values they need. Why? Because it says here the x values. And how would I do that? Well, therefore I would say that my x is in. Now I would do -1 to 5. Does it include those values? No, because at -1 there's a 0 gradient, at 5 there's a 0 gradient. So that is just going to be curved brackets. And believe it or not, that's the answer to the first part. What about the second part? We want f dashed of x is less than 0. And again, you can download these notes from mathsguru.com. Yeah, stop the video, download them, write all over it, because I may not be writing enough for you. And bearing in mind you're allowed a summary book, you can actually put a lot of this in your summary book and life becomes easy for you. All right, so what do we got here? F dashed of x is less than 0. Oh my God, panic. No, don't panic. It's fine. This basically just means negative. Where are all the points on here that are negative? Now, what you tend to notice is there's two sections of the graph. There's this section of the graph is negative, and that section of the graph is also negative. So how do we describe that? Well, again, we use interval notation, but. So what I'm going to say is I've got all values of x, which are in now. Well, this seems to go to infinity and beyond. So I'm going to say minus infinity, comma, -1, close bracket. So that's going to take the interval from this -1 here all the way to negative infinity. Then I've got to have from my value of 5 all the way to positive infinity. So then I'm going to do brackets, 5 to positive infinity. And remember, infinity always has a curved bracket because it's more a construct. It's an idea rather than an actual number. Now, a lot of people make mistakes here and then they go and. It can't be and. And in maths means that they overlap, right? There's an intersection between the two. And basically the numbers minus infinity to -1 and 5 to infinity do not overlap. None of those numbers overlap. And so it's important you put union, which is or, right? Because x can't appear in both of those. X can't have values that fall in both of those. That's why you can't use the and. And likewise, if we had f dashed of x is equal to 0, then in that situation we would say x is in, and we would do a set notation because it is just two values, -1 and 5, and then close my curly brackets. I'm really bad at drawing curly brackets, but again, I've seen this in so many exams that has tricked so many people just because they see this f dashed of x is less than 0 and believe it's a point. Now we're going to move on and then turn around and say, right, now I want to draw a differential graph, a graph of the differential of a function. And in this particular instance here, and thank you very much Cambridge for allowing me to use your textbooks. Sadly, I can't get rid of the green background. That frustrates me, but anyway. All right, but in this situation, how am I going to turn that? Well, while we're not going to get this exactly correct, what I do know is that where there is a maximum or a minimum, there's going to be a gradient of 0. So first thing I'm going to do is that's f dashed of x, and here is my values of x. So I'm doing my graphs, where is there a 0 gradient? Oh, very helpfully, they've given me the point 3, -1. Don't care about the -1, it's the 3 that's important. So I'm going to do a mark there at 3, and I automatically know that at that point there is a 0 gradient. What do we notice about the gradients of that part of the line there? So the left-hand side of 3. Well, they're negative. Are they? They're negative, yeah? Getting more and more or closer and closer to 0, yeah? So they're negative but getting less and less and less negative. So what I want you to think about is the section under the graph means negative and the section above the graph means positive. And so, what are we going to have here? So it's getting closer, so we're going to have a negative gradient. So there's going to be something down here. And then on this side here, it's going to be from 0 getting more and more and more positive. And it's going to go off to infinity and beyond. So there's going to be maybe a point up here, but what's it going to look like? Well, this is again where you say, well, the graph here, the section they've shown, and assuming that's right, is basically a y equals x squared graph. That's a parabola. Now, when we differentiate this, what do we get? We get 2x. We get a straight line. So the gradient of a parabola is basically going to be the equation of a straight line. And so in this situation, I know that that there must be a straight line going to infinity and beyond on both sides, right? So again, when we have a parabola x squared, it becomes a straight line, really important. What about this one here? Right, so again, a bit of a trick question, but I've seen these come up in maths so many times. There's x, I now want f dashed of x. Rightio, it's impossible to determine all the features, and again, that's important, but what are we trying to find? We're trying to find the gradient. Now, it's not a curve, All right, so there's no zero, there's not a lowest point or a highest point, it's a straight line. How on earth do I find the gradient of a straight line? Gradient of a straight line, we can do that. It's rise over run. So we know the rise here is 1, we know the run there is 1, so in which case my gradient is 1 on 1, which is 1. And because it's a straight line, what do we know about the gradient all the way across that line? It's exactly the same. So in which case, actually in that situation, I'm just going to have a horizontal line through the value of 1, because it doesn't matter what value of x I choose, the gradient all the way along that is going to be the same. And in fact, because they've given me these points here, it then helps me find the gradient of 1. That question I've seen trick so many people. Now this last example before I move on says, oh, well now we've got another. Draw the function of x for each of the following. Well, I'm going to turn around and say, well, what, roughly speaking, what could that function be? Right? It's probably some sort of a cubic. So that means my y dash is going to be some form of a parabola. So before I go any further, I now know that my graph is either going to look something like this or something like that. Which one? Don't know at this moment in time. Let's work it out. F dashed of x, and there's x. Now, what am I going to do? Well, it's a curve. It's some sort of curve function. Do I have maximums and minimums? I absolutely do. I've got a maximum here, which means I have a 0 gradient at minus 1.5. So there's minus 1.5. I've got a 0 gradient. I've got another one here at 1. So I now know if I have my coordinate of 1 there, I've got a 0 gradient. Now again, these are positive gradients above the line and negative gradients below the line. So let's look at this section here that I'm highlighting, he says. So the left-hand side of minus 1.5. Are my gradients positive or negative? Well, they are sloping up, but actually they're getting less and less and less. So they're going from pretty big positive to smaller and smaller and smaller positive. So it would suggest that my line has got to go like that. Now, to be honest with you, I don't really need to worry about the rest of it because I know that I've got some sort of a cubic which differentiates to a parabola. I've got an idea of where the first part of the parabola is, and so actually I'm just going to finish it off like this. But let's just check. The value of my gradient between minus 1.5 and 1. So between minus 1.5 and 1, that one there is negative. Now again, you've got to think about what's actually happening there. It's going from a really small negative, it's getting more and more and more negative until some point where it's got to come back to 0, yes? So it's gone a little bit negative to more and more negative to less negative and back up to 0. So that's what's being described here. A little bit negative, getting more and more negative to some sort of point and then going back up. Now, normally with a parabola we could find the minimum, but that's what the question is saying here. It's actually not possible with the information that we have to determine all the features of this parabola. But again, if we now look at the points from 1 onwards, what do we notice? They are all positive gradients, all right? So everything above the line. And it's, as it's moving further away or further across the x-axis, the gradient is getting more and more and more positive. And so there we go. This is great to practice, right? It's one of those things we put in exams just to see whether you understand what you're doing, really, rather than regurgitating. Now, some of the language we use in maths is relating to strictly increasing and strictly decreasing, right? Whether a function for 2 given points is increasing or decreasing. Now, the way we do that is we basically go and we compare 2 points, f of a and f of b. Now again, if you understand that notation, the rest of this makes a lot more sense. This is basically saying I've got an x coordinate of a and an x coordinate of b. And ideally they're going to be relatively close to each other, side by side, all right? And what we're saying is, well, f of a is the y value at a. So f of a is basically the y value at a. And f of b is the y value at b. So let's do y of a and y of b. So what we're doing is we're comparing. For some function, let's look at where the y values are. And what it says is, it's going to be strictly increasing when your f of a is less than f of b. Now what that means is the y value of b is slightly higher than the y value of a. So that could be my y value of a. There is my y value of b. It seems that the graph there is increasing, all right? So that's awesome. Makes sense, hopefully. And again, it is strictly decreasing when f of a is greater than f of b. That means the y value at a is bigger than the y value of b, and it's decreasing, right? So that is the rule for strictly increasing and decreasing. All right, and we use that again in maths ever such a lot. There is another test we can do. We can sort of look at the differential, and we can generally, for some functions, say, well, when f dashed of x is greater than 0, i.e. we have a positive gradient, then it is strictly increasing. But that doesn't actually work for all graphs, and there is an example here. So basically, when we have y is equal to x cubed, as it turns out, when I look at the gradient at the point 0, believe it or not, it comes out as 0. So in that situation, f dashed of x is greater than 0, not at that point there. So it sort of falls apart, which is why it probably makes more sense to always just look at two x values, find the y values, and then sort of test to see whether it's increasing or decreasing that way, because maths is sadly a big fat trick. Now, the last part of this video goes on to say about angles of the gradient of a curve at a point. Believe it or not, we seemingly get very obsessed in maths about angles and gradients, you know, with respect to the x-axis. So if I put a point here and draw a tangent to that point there, believe it or not, I can actually find the angle that tangent makes with the x-axis. You're going to turn and say, why would you need to do that? I have no idea, guys, to be perfectly honest with you, but it seems to be there all the time, right? Now, we've got a gradient, yes? We got a straight line there. So taking that straight line, I've just drawn it there. What do I know? Well, I know the gradient of a straight line is given by rise over run. Yes, that's just the gradient of a straight line. But hold on a moment. This angle here, when I do rise over run, is tan theta. So if tan theta is equal to rise over run, which it is because it's opposite over adjacent, and we know that the gradient of a line is equal to tan theta, then actually we know the gradient is equal to tan theta, because if m equals tan theta and in tan theta and gradient is equal to, then basically m equals tan theta. Oh my goodness, m equals tan theta. Now you're going to try and say, well, what's that got to do with the price of fish? Probably nothing. I don't know who prices fish nowadays. But what I'm saying is, if I can find the gradient at a particular point, wonder what I could use to find the gradient at a particular point, then I can find the angle, because I therefore know that theta would be tan to the minus 1 of whatever my gradient is at that point. Oh my goodness. So let's see if I've got some examples. Find the coordinates of the point on the curve with equation at which the tangent line 1 makes an angle of 45 degrees. Right. So they want theta equals 45 degrees. Well, hold on a moment. We know that m is equal to tan theta. So m is going to be equal to the tan of 45. And we know that that gives me a gradient of 1. So find the coordinates for the points on the curve with equation at which the tangent line basically is 1. Find the tangent is 1. Well, how do I do that? Well, I've got y is equal to x squared minus 7x plus 8. So we know therefore that dy by dx, which is my gradient function, gives me 2x minus 7. And we're basically trying to find the x value where m equals 1, or the gradient equals 1. So I know that 1 is equal to 2x minus 7. 2x becomes equal to 8. X becomes equal to 4. So there we go. On that gradient function, there is only one point where it has a gradient equals to 1, and that's the x point is 4. Now, word of warning. The question actually says find the coordinates. And again, methods is a flipping massive trick, because when it says coordinates, it wants both the x value and the y value. So having found the x value, I would then substitute it back in here and find that my y value is going to give me 16 minus 7, 14, 21, 28 plus 8. So 16, so that's going to give me minus 4 if I've done that correctly. 16, yeah, all right. So again, you would have to give your coordinates then as 4 comma minus 4. Believe it or not, I'm actually just going to fire up my calculator. I know that sounds a bit silly, but I'm going to fire up my calculator and just check that that's actually right. All right, doing that, let's just do a calculator. You're going to turn around and say, are you absolutely sure? I don't want to record this video, believe it or not, and then have to re-edit it later just because I've made a silly calculation error, and it is in fact minus 4. Job done. Right, is parallel to the line. So now on the second point is parallel to the line y equals minus 2x plus 6. Y equals minus 2x plus 6. Well, if it's parallel to that line, it must have the same gradient. And I know the gradient of this line is minus 2. So again, they're just coding this question. So we're trying to find the point where m is equal to minus 2. Well, I've already done the hard work here. I already know the differential of that equation. So in which case now, I'm just trying to find out where 2x minus 7 is equal to negative 2. So I get 2x is equal to minus 2 plus 7 gives me 5. And so x is equal to 5 on 2. All right, firing up my calculator. Absolutely not doing this in my head. So what have I got? I'm going to do, what is it, 5 on 2 squared. So 5 on, 5 on 2. Bear with me while I try and get my fingers to work. Minus 7 lots of 5 on 2. Oh, I do know what I'm doing, I promise. Plus 8, which gives me minus 13 on 4. So my coordinates would be 5 on 2, comma, minus 13 on 4. Yeah, that took longer to use my calculator than anything. Okay, so the planned path for a flying saucer leaving a planet is defined by that equation, where this is going to be y and that is going to be x. Now, again, here is really, really important. Methods loves to give you restricted domains. In many cases, it's because in this situation here, we can't have negative values of x. But later on, particularly throughout the course, where you've got a choice, you're going to have to decide which is the right one to use and look at the domain. The units are in kilometers. Find the direction of motion when the x value is 2. Now, when it talks about direction of motion, it's actually talking about the angle, right? So it wants the angle for some strange reason, brand new to me. So the direction of motion when the x value is 2. So the first thing I'm going to do is I've got y is equal to 1/4 x to the power of 4 plus 2/3 x cubed. So I know that y dash, which is my differential, is going to be multiplied by the power. So 1/4 times 4 is 1. Take 1 off the power, it gives me x cubed. Plus, well, again, that's going to be 2/3 times 3, which is going to be 2. That's going to be 2x squared. So what is the direction of motion? So in which case, I now want the value of x is equal to 2. So I'm going to write that y dash, which is otherwise my gradient, and I'm going to write that as n just to give me a hint, is equal to 8 plus 2 times 2 squared, which is 8, which is going to give me 16. All right, so there we go. We've got 16, and in which case we now know that we want to find tan theta is m, or theta is going to give me tan to the minus 1 of 16. And so what am I going to end up with there? Fire up my calculator. Trig, 10 to the minus 1 of 16, I'm in degrees. 10 to the minus 1 of 16, I'm in degrees, and I'm also in exact values, so let's have that there. So in which case we would have theta is equal to 86 point, I know we'll do it to 1 decimal place, 86.4 degrees. And what would we do for part 2? Well, when x is equal to 3, what do I have? I would have y dashed, which is equal to m, is going to be 3 cubed, which is 27, plus 2 lots of 3 squared, which is going to be 9, 18, 27 plus 18. Again, I am embarrassed, 27 plus 18, only because I don't want to make a mistake, is 45. So we want theta is equal to tan to the minus 1 of 45, which gives me, and again, sorry about the lack of space here, tan to the minus 1 of 45, which again, he says, wishing desperately to change, is 88.7 degrees. Moving on to the next part of the question, I needed a little bit more screen to illustrate. So let's find a point on the flying saucer's path where the path is inclined at 45 degrees to the positive axis. Well, again, they've given me 45 degrees. So we know there that m is equal to tan theta. So my gradient's going to be tan of 45, which again, I just so happen to know is 1. How does that help me? Well, again, I know that y dashed was given by x cubed plus 2x squared. I now know that y dashed and m are interchangeable, they're the same thing. So in which case I know I'm trying to solve for when x cubed plus 2x squared is equal to 1. How do I do that? Oh, I don't know. Would you reckon I'm going to fire up my calculator? I should go, okay, so I'm going to solve in this situation that x cubed plus 2x squared. And again, this is a CAS course. Why do the hard work when you don't need to? And what do we get there? So we get my x value is equal to, now, this is a point in fact. Do you notice what your calculator's giving you there? It's giving you 2 answers. Now again, many people, or is it actually giving me 3 answers? My apologies, too far away. It's giving me 3 answers. So the question is, are all those relevant? No, and that's where we come back to our domain. Always check to see where there's a limitation. So in this situation, x has to be greater than 0. So if we look at my values here, what I got? Negative 1.6, no good. Minus 1, no good. So in which case, x would have to be that value there. So x is going to be equal to 0.62 if we round that to 2 decimal places, all right? So find a point on the flying saucer's path where the path is inclined at 45 degrees to the positive axis. There we go, x is equal to 0.62. Now again, is that asking for a coordinate? Not specifically sure. If I needed to, I would then put that x value back into this equation here and find my coordinate. Part C, are there any other points on the path which satisfy the situation described in part B? Well, yes, but for the part of the graph that actually isn't given to us. So yes, you could put down and say, well, yes, x equals minus 1, but actually no. The correct answer, I suppose, is no, because of our limited domain. What you'll notice here is the graph was very important. And my biggest advice I give to all of my students here is when they give you a function, sketch it. When you can see what it looks like, it makes life so much easier for methods. Well, I'm pretty sure that there is the end of this video. Thank you very much for watching. Hopefully it has been useful, and there are other videos in the series coming. If there's anything more I can do, leave a note below if you're watching on YouTube. Leave me a comment, sign up to YouTube if you can. Again, it means the world to me. Follow me on TikTok and go to maffsguru.com. There are other videos in the series which hopefully I will see you in. If not, you take care. Please stay safe. Until the next time. Bye-bye.